Okay, this is section 5.5 and we're talking about trigonometric equations, specifically solving trigonometric equations, and what we run into when we're doing those. A trigonometric equation is an equation that contains a trigonometric expression with a variable such as sine x. We've seen some trigonometric equations are identities, such as sine squared x plus cosine squared x equals 1. These equations are true for every value of the variable for which the expressions are defined. So, for instance, no matter what value we choose for x, sine squared x plus cosine squared x is going to equal 1, always. In this section, we're going to consider trigonometric equations that are true only for some values of the variable. The values that satisfy such an equation are its solutions. Remember, solutions are just what makes an equation true, a true statement. So we're going to look for any values that make the equation true. Now, there are trigonometric equations that have no solution. For instance, sine x equals 2. This is an equation that there is no angle you can put here, because remember, sine x, the sine value of any angle is going to be between -1 and +1. So this equation right here has no solution because there is no value of x you can plug in there where the sine x is going to equal 2. So that's an equation, or that's an example of a trigonometric equation that has no solution. All right, now, equations involving a single trigonometric function are easy to solve. All you're going to do is you're going to solve an equation, you're going to isolate the function on one side of the equation, that means get it by itself, and then you're going to solve for the variable. So in this case right here, I've got sine x and sine x on both sides, and I've got values on both sides. So what I'm going to do is I'm just going to move them back and forth and get all the signs on one side and all the non-signs on the other side. So, and when I say non-signs, I mean non-trig functions. So I'm going to move the 3 sine x over here. So I'm going to subtract 3 sine x from both sides. And I'm going to add 1 to both sides to get rid of this 1. So 3 sine x minus 3 sine x goes away over here. -2 plus 1 gives me -1. 5 sine x minus 3 sine x gives me 2 sine x. And -1 plus 1 gives me 0. So now I've got 1 sine x on the right side. Doesn't matter if it's right or left. And then I want to solve and isolate the sine x. So I want to get rid of even the 2. So I'm going to divide both sides by 2. So I'm looking at -1/2 equals sine x. Now I want to find, and I'm going to rewrite this, I'm going to flip things around. I want to find every value of x that's going to give me a sine value of -1/2. Now when you do that, you got to understand there's lots of values. So, but what we want to find is we want to find the ones, we're going to limit ourselves for right now just because we need to have a limit. All the values between 0 and 2 pi, for which if I took the sine of that angle, it would give me -1/2. So sine values are the y values, remember. So sine values are going to happen that are negative in quadrant 3 and quadrant 4. So I'm looking for the pi over 6's in quadrants 3 and 4. So x is going to equal 7 pi over 6 and 11 pi over 6. Now these are x values that are going to give me an x value or sine value of negative 1/2. There's only one problem. If we're looking for all solutions, this is not going to give me all of them, because I'm also going to have to go from there and there. Once I get around one time, I can go back around and get to the same thing. Remember those coterminal angles? Every time I get back to that one place, as I go around and around and around, what am I doing? I'm finding the exact same sine values and cosine values. So if you're not specifically told to find them from 0 to 2 pi, what you end up doing is adding a little something. Let me slide that over just a bit. And you're going to add the period. 2 pi times n, where n is just going to be an integer. It's a counter. It's like 0, 1, 2, 3, 4, all those. But that's just saying 7 pi over 6 and every other rotation around to get back to the same place that I have. 2 pi n, if 2 pi is 0, I'm at 7 pi over 6. If n is 1, I'm at 7 pi over 6 plus 2 pi, which tells me I go around to there and then I go around again and I get back to the same value. And you're going to have the same exact thing with this other one, so you have to have it with both of them. Realize that 7 pi over 6 plus 2 pi n is not 11 pi over 6. So you have to list both of the ones that are on the 0 to 2 pi. Then, if you're including all solutions, you're going to add the 2 pi n. But the biggest thing is you're going to have to know values on the unit circle backwards and forwards so that you can figure out what angles would give you a sine value of negative 1/2. Alright, now for equations that involve multiple angles, the angle is a multiple of 3 here, the angle is a multiple of 1/2 there. You solve each equation just like you normally would for 0 to 2 pi, and the period of the function plays an important role in ensuring we do not leave out any solutions. So you're going to have to remember what the period of this thing is. So find the period, and that's what you're going to multiply by n and add to it over and over and over again. Alright, so let's solve this equation. Tangent of 3x equals 1. Alright, first thing, you're going to have to take the inverse tangent of both sides, or think about what value of tangent gives me. So, what angle is going to give you a tangent value of 1? So, 3x is going to have to equal pi over 4, and in quadrant 3, we're going to have 5 pi over 4. Both of those give us tangent values that are exactly positive 1. Quadrant 1 because sine and cosine are both positive. Quadrant 3 because both sine and cosine are negative. Now, then what we're going to end up doing, we need to find out exactly how far what our period is going to be. And if you remember, the new period is equal to the old period divided by b, which in this case is 3. So the new period is going to be 2 pi over 3. Well, 2 pi over 3 is going to be smaller than the old period. Sorry, that's wrong. Wrong. The original period for tangent is pi, so we end up with the new period being pi over 3. So pi over 3 so what that means is that's what I can go in here and I can add. So 3x is going to equal pi over 4. And since this is outside of pi, I don't want to worry about that. I'm just going from 0. I'm worried about my solutions from 0 to pi, because after that they're just going to occur every pi. It'll make sense in just a second. I'll go back and explain it and clarify what I just did and why I marked that out. All right, and then that's going to be plus n pi. Now, when I go and solve this, I'm not looking for what 3x is. I'm looking for what x is. So when I solve for x, I'm going to have to divide everything here by 3. Everything on that side and everything on that side. So x is actually going to equal pi over 12 plus n pi over 3. So that is what your solution is. Now, the reason why I marked out the 5 pi over 4 is because I was thinking and on the idea of the 2 pi here. You got to remember that tangent has a period of pi. So I'm only looking for the solutions between 0 and pi. Any solutions in there, and then I can finish solving this. And this part right here is going to pick up and take on all those right there. So to find the values from 0 to 2 pi, we're going to finish this problem out in just a second. Remember, this is all the solutions. I'm looking for the ones only between 0 and 2 pi. I limited myself when I did my initial solution from 0 to pi because this is the period, the original period of tangent. Once I get my initial values, then I'm going to solve for x, and then my final answer, I'm looking for x to be somewhere between 0 and 2 pi. The x right here is not really the x. The x right here is this thing. So all I'm looking at here is I'm saying this thing right here is going to be between 0 and pi because that is a single period of tangent. That's all I'm doing. So that's why I only found the pi over 4 between that made this true from 0 to pi. I threw out the 5 pi over 4 because it was outside of this. Now, once I get my all solutions, I can limit it down to just these. So I'm looking for all the ones, I'm going to add n, the n pi over 3, but I'm only looking for the ones between 0 and 2 pi. So of course I know pi over 12 is, and that's with 0 pi over 3. If I add pi over 3, it's the same as adding 4 pi over 12, right? Common denominator and everything. So 4 pi over 12 plus 4, pi over 12 plus 4 pi over 12 will give me 5 pi over 12. Then I'm going to add that again and do it 8 pi over 12 because it's 2 pi over 3. And that's going to give me 9 pi over 12. And then I'm going to add again, and that would be pi, or 12 pi over 12, which will give me 13 pi over 12. And in case you haven't caught on, I'm adding 4 pi over 12 each time. And then continue on, that would be 17 pi over 12. And once I add again, I'm going to get 21 pi over 12. And then add 4 again, I'm going to get 25 pi over 12. And I'm going to stop, then I'm going to erase this one. I'll explain why in just a second. So remember, all I'm looking for is the final answers between 0 and 2 pi. Once I get to 25 pi over 12, I know this fraction right here in front, ignoring the pi, is greater than 2. So I don't need that answer. I'm done. I don't go any further. So it's just those solutions right there. So these are all the x values between 0 and 2 pi that when you plug into this equation, the tangent of 3 times whatever that thing is going to be 1. Alright, so let's solve the equation sine of x over 2 equals the square root of 3 over 2, and we're looking for all x values between 0 and 2 pi. Alright, so remember I'm looking for x over 2, and what's the period of sine? It's from 0 to pi, right? 0 to 2 pi. So we're looking for all the solutions between 0 to 2 pi of x over 2. So if I do sine of x over 2 equals the square root of 3 over 2, what are all the places on the entire unit circle where I can get a sine value that's a positive square root of 3 over 2? So what are they? Well, we know in the unit circle, sine's only going to be positive in quadrants 1 and quadrant 2. And what are the ones that are going to give me a square root of 3 over 2? Well, they're going to be the pi over 3's. So we know that x over 2 is going to be pi over 3 and 2 pi over 3. Those are the pi over 3's in quadrant 1 and quadrant 2. Now, we know that we've got 2 pi as the period, so x over 2, if we're looking for all solutions, is going to be pi over 3 plus 2 pi n, and 2 pi over 3 plus 2 pi n. Now then we're going to solve for our x, which means we're going to multiply everything on both sides by 2. So x is equal to 2 pi over 3 plus 4 pi n and 4 pi over 3 plus 2 pi n. Now, then we can go back and look. We're looking for all the solutions of x, or all the values of x that would work between 0 and 2 pi. So 2 pi over 3 is going to be one of them. So x is going to equal 2 pi over 3. And here's the thing, if I add 4 pi in, if I add 4 pi, am I going to be outside of 0 to 2 pi? Yeah, of course I am, because I'm adding a whole 4 pi to something that's already positive, so it's going to be greater than 2 pi. And the same thing over here with 4 pi over 3. If I add another 2 pi, oops, sorry, that should be 4 pi, because I multiplied all the way through by 2. If I add another 4 pi to that, I'm definitely going to be larger than 2 pi. So we're looking at 4 pi over 3 there as well. And those are the only two values between 0 and 2 pi that the sine of x over 2 is going to equal the square root of 3 over 2. So that's all you're doing. Limit your initial solution before you solve for x itself. When you solve for the thing you're taking the trig function of, limit yourself to the period of the original function. And then, once you've solved that and found every solution with the plus period times n, then you're going to solve for x, and then you're going to go through and check and see how many different values you're going to have between 0 and 2 pi, or 0 and 4 pi, or 0 and 6 pi, whatever. They can change change numbers on that. So pay attention to what you're looking at. All right, now some trigonometric equations are in the form of a quadratic equation, au squared plus bu plus c equals 0, where u is a trigonometric function and a does not equal 0. Here are two examples of trigonometric equations that are quadratic in form. 2 cosine squared x plus cosine x minus 1 equals 0. 2 sine cubed x minus 3 sine x plus 1 equals 0. Now, what you want to do is you want to actually go in and put a u in for each of the trig functions. Now, these trig functions have to match, otherwise this method doesn't work. So when you do that substitution in, it's going to look like a polynomial. It's going to look like a regular quadratic that you can factor. So you're going to try to factor it. If it'll factor, then you solve each individual factor the same way we have so far with just the regular equations. So let's look at one of these. Alright, so we've got 2 cosine squared x plus cosine x minus 1 equals 0. And we're looking for all solutions of x between 0 and 2 pi. So I'm going to rewrite this thing first. And u, I'm just letting u equal cosine x. So cosine squared x is just cosine x squared, so that's u squared, plus cosine x, which is just u, minus 1 equals 0. Now I'm going to factor this. So 2u squared plus u minus 1, I'm going to do bottoms up, so I'm going to move that to the end and multiply to get u squared plus u minus 2. I'm not going to do the equal 0 because technically it's not the same equation anymore, so it's not equal to 0. I'm going to factor this. We're going to have u there, here u there, u everywhere, u. So we're going to have minus at the end here, so that means we're going to have opposite signs, 1 plus, 1 minus. Factors of 2 that will subtract to give you 1, it's going to be 1 and 2, and this sign means the larger one goes with a plus. Right, and then whatever number I multiplied by here, I'm going to divide both of these numerical terms by there. 2 over 2 equals 1, so we get u plus 1. And over here we're going to have nothing that's going to reduce, so the 2 comes out in front of the u, and we end up with 2u minus 1. Now, this is back to the normal function, so I can go ahead and put equals 0 there. Now I can go back and put my cosine in, so I know cosine x plus 1 times 2 cosine x minus 1 equals 0. So now, the same way we would with any other factoring situation we deal with, we're just going to take each one of these and set it equal to 0. So moving over here, I'm going to change colors just so it doesn't get confused. I've got cosine x plus 1 equals 0, and 2 cosine x minus 1 equals 0. So I'll move the 1 over, so cosine x equals negative 1. What angle is the cosine x equal to negative 1? Well, that's going to be x being equal to 3 pi over 2. No, sorry. Pi, sorry. And then over here, 2 cosine x minus 1 equals 0. I'm going to move the 1 over. 2 cosine x equals 1, divide by 2. So we're looking for what value of x gives me a cosine x of 1/2. Well, that's going to be in quadrants 1 and 4 for where x is positive. And where cosine is 1 over 2, it's going to be pi over 3s. So that means we're going to have x is equal to pi over 3. And what's the pi over 3 in quadrant 4? Well, that's going to be 5 pi over 3. Alright, so here are all my solutions from 0 to 2 pi. So I don't have anything special to deal with, so there's all my solutions. I just write them all down. You typically want to write them in order. So pi over 3 would be the first angle that comes first, and then pi would be the second one, and then 5 pi over 3 is the third one, since it's the largest of the three. Alright, let's do this one again, or do another one of these. We got 4 sine squared x minus 1 equals 0. So I'm just going to plug in u in place of the sine x. So I'm letting u equal sine x. And I can factor this into 2u minus 1 and 2u plus 1 equals 0. Because I know that's a difference of squares. That's a perfect square, that's a perfect square, so it splits up this way. So then I can put my sine x back in. So 2 sine x minus 1 times 2 sine x plus 1 equals 0. Once again, take each one of these, set it equal to 0. and then just solve for the sine x. Isolate your trig function. So I'm going to move the 1 over and divide by 2. So I'm going to have sine x for the first one equals 1/2. Second one, move it over, get a -1, so I'm going to end up with sine x equals -1/2. So I'm looking for all values on the unit circle that are going to give me a sine value of 1/2. So the ones with a positive, remember those are quadrants 1 and 2. So that's going to be the pi over 6's. We're going to have pi over 6 and 5 pi over 6. And then over here, the x values are going to look at the ones that are going to give me a -1/2, which are still the pi over 6's, but these are in quadrants 3 and 4. So we're going to equal 7 pi over 6 and 11 pi over 6. So all my solutions are all the pi over 6's on the unit circle. Pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. Hopefully you can see by now how important it is to know your unit circle. Guys, I've told you there's not going to be a calculator that you can use on this test. So you're going to have to know those off the top of your head, or draw a unit circle right after I give you the test or something. Because you cannot have a unit circle on the test. Alright, now we've seen that factoring is used to solve some trigonometric equations that are quadratic in form. Factoring can also be used to solve some trigonometric equations that contains two different functions, such as tangent x sine squared x and equals 3 tangent x. In such a case, be careful. Make sure you read this. Move all terms to one side and obtain 0 on the other side. Then try to use factoring to separate the different functions. Now, the reason I say that, some of you guys are going to come in here and you're going to say, oh, well, I'll just divide by tangent. And now what happened? Well, your tangent goes out completely. And I've solved this so quickly. I'm looking for where sine squared x equals 3. No, you just eliminated some of the solutions. We're looking for where tangent x times sine squared x equals 3 times tangent x. When you do this, you're eliminating all the solutions that would come from the tangent. So you can't do that. What you would do, you got tangent x sine squared x equals 3 tangent x. You're going to move that to the other side, not by division, by addition and subtraction. Tangent x sine squared x minus 3 tangent x equals 0. Once you get it equal to 0, then you can factor. And we have a common factor of tangent x. We got tangent x factored out. And we got sine squared x minus 3 left inside equals 0. So then we just look at where we do it exactly the same way we did the last one. We set each factor equal to 0. So tan x equals 0. Our sine squared x minus 3 equals 0. And then you just solve those individually. So, we did all that. So let's go ahead and work it out. Hold on just a second. Alright, so copying the stuff that I just written down from the last page over onto this, you get to this point again. So we got tangent x equals 0 and sine squared x equals minus 3 equals 0. Take each one. So tangent x equals 0. What values? Well, here's the thing. Think about it this way. You know tangent x is sine x over cosine x. So the only way this is going to equal 0 is if the top's equal to 0. So where is sine x equal to 0? Well, sine x is equal to 0 when x equals 0 and x equals pi. And 2 pi. Even though we're not actually including 2 pi, I like to go ahead and include it. So we've got 0, pi, and 2 pi. And the reason why a lot of times you want to include 2 pi because 0 is going to be included when you do the plus 2n pi. Alright, now over on this one, we'll come back to this in just a second. We've got the sine squared x minus 3 equals 0, so you're going to move the 3 over. So you've got sine squared x equals positive 3. Take the square root of both sides. We're looking at sine x equaling the square root of 3. And what do we know about sine x? Well, sine x is always going to be between negative 1 and positive 1. What's the square root of 3? Well, the square root of 3 is definitely greater than 1, so we know that there are going to be no solutions from this. So x equals no solutions over here. There are no solutions that are coming from this part. So these values over here are the only values that are going to make this thing true. So x equals 0, pi, and 2 pi. And since you don't include 2 pi, you could actually take that out. 0 and pi would be fine. If you include 2 pi, I'm not going to take off from it. Now if this is equal to also, you've got to include the 2 pi. Remember, that means that you're from 0 including 0 all the way up to 2 pi including 2 pi. Without the equals, then we're just going up to but not quite getting to 2 pi. Now, some trig functions or trigonometric equations contain more than one function of the same side. These functions cannot be separated by factor. You can't factor a cosine out. There's not a common cosine. What you can do is use an equivalent expression of one of these for it, for instance, a trigonometric identity. So we can use the identity sine squared x plus cosine squared x equals 1, and with a little rearrangement inside for cosine squared x, we can put in 1 minus sine squared x. Okay, and that's what we're going to do on this equation. So let's go ahead and work this out. Alright, so 2 cosine squared x plus 3 sine x equals 0. When we see this, we know we can't deal with two different trig functions and do any kind of factoring like that unless they're in all the different terms, and they're not. So what we want to do is we want to take the cosine squared x, and we're going to replace that because we know cosine squared x equals 1 minus sine squared x. That's just an adjustment of a Pythagorean identity, sine squared x plus cosine squared x equals 1. So in place of cosine squared x, remember if these two things are equal, they're interchangeable. So I can do 2 times 1 minus sine squared x plus 3 sine x equals 0. And all I did was plug that in place of the cosine squared x. So when I distribute this through, I'm going to have 2 minus 2 sine squared x plus 3 sine x equals 0. Alright, so now I've got one that is in a single trig function. So I can go back and I can treat this thing like a quadratic like we did before. So I'm going to rearrange everything and bring that to the sine squared out front. Negative 2 sine squared x plus 3 sine x plus 2 equals 0. And I'm going to multiply through by negative 1 just because I don't like this negative 2 out front. I'm going to multiply the entire equation by negative 1. It's just going to change all the signs. Yeah. So that's going to give me 2 sine squared x minus 3 sine x minus 2 equals 0. So now I want to factor this, doing bottoms up. So multiplying, so we end up with sine squared x minus 3 sine x minus 4. So then I'm going to factor this. I can go ahead and put in a u if I want to, but I'm going to, you don't have to. Once you get comfortable with this, you can do it without doing the u. I'm going to do it without the u. So sine squared minus 3 sine x minus 4. I'm going to have sine x and sine x. It's just replacing the u's or the x's like we normally factor. This thing right here tells me I'm going to have opposite signs, 1 plus, 1 minus. This tells me the larger of the two numbers is going to go with a minus. So what numbers multiply to give me 4 and subtract to give me 3? Well, they're going to be 4 and 1. This tells me the larger number goes with the minus. Alright, and then whatever I multiplied by here, I'm going to have to divide by here. So when I do that, I'm going to have nothing to reduce right here, so the multiple of 2 is going to come out front. So I get 2 sine x plus 1. Here I'm going to reduce that to 2. So I get sine x minus 2. And now that I've done my bottoms up, I can bring back the equal 0. Alright, changing colors just so I can keep it separate a little bit here. Actually, let me scroll down just a little bit. I may have enough room. Alright, so if I set this equal to 0, 2 sine x plus 1 equals 0, and sine x minus 2 equals 0. Right here, if I move the 1 over, it's going to become negative. Then I divide by 2, so I'm looking for values of x that make sine x equal to negative 1/2. We've done that already, but we'll go ahead and list them. What do we know about negative 1/2? Sine being negative means that we're going to be in quadrants 3 and 4, where y is negative, and the ones that are going to make the trig function be a 1/2 are going to be the pi over 6's. So we're looking at 7 pi over 6 and 11 pi over 6. Now over here, when we go to solve, we're going to move the 2 over, and we're looking for what value of x is going to make sine x equal to 2. Well, once again, sine x is always going to be between negative 1 and positive 1, so it's never going to equal 2. So we have no solutions from that side of the equation, or from that factor. So there is the only answers to this problem. Alright, that's it.